Okay, let's get started the afternoon session. Our afternoon speaker, second speaker of the day, is Aleksey Cherman from Minnesota. We're very happy to have him. I just sounded like a trumpeter.
Thank you for your attention.
Yes. Yes. And he will tell us about symmetry theta angles. Whenever you're ready, please take over.
All right. Can you all hear me? I think the microphone sounds like it's on.
Yeah.
Okay, great. So the first thing I want to say is a great thank you to the organizers of this workshop. It's been enormous fun. I've learned a ton, and I'm very grateful to have the opportunity to give a talk. Please interrupt me with questions, as you've been doing to all the speakers. I'm going to enjoy it. What I'm going to do today is to tell you about some work that I've been doing with a person who's in the audience, Maria. Okay, this is Maria. And also two spectacular postdocs. Aleksey Cherman, who's at Minnesota and is officially working with me, although he's a kind of a free-ranging postdoc as well. And Dongjun Choi, who's a particle phenomenologist. And in the stuff I'll talk about today, I'll dip into this paper with Dongjun a little bit. And most of it will be about this stuff with Maria and with Xu. Okay. So the plan, which is very rough, is I'll start by trying to motivate the questions that I want to ask and the kind of answers that I will supply, and some kind of introduction. Then I want to go through something that we're going to call discrete symmetry theta angles. You don't know what that is yet, don't worry, you're not supposed to. And that is intended to cover something like the first half. We'll see, maybe it's the entire thing. And if we get there for the second half, maybe or not, it's okay if not. Maybe we'll talk about continuous symmetry theta. Again, whatever those are, you'll see them. Okay, so let's get going. So what I want to start with is just so we're on the same page. Like, what's a theta angle? What do we need? So here's the conventional picture. So the conventional picture is theta, a theta angle, is a typically 2 pi periodic parameter, okay, which appears in the path integral, multiplying something topological. Okay? And in the most familiar cases, of course, this S topological is nothing very mysterious. But for example, in Yang-Mills theory, this would be the usual topological number property. And the key thing about whatever this quantity is that in the simplest example, so just an integer on any field field. Right? Now, there are more sophisticated examples of theta angles in field theory. They could be discrete. We heard about some of those, I think, in some previous talks. And some of the ones I'll talk about will also be discrete, although a little bit different than we'll normally do. But the simplest ones are these. Right? So everybody okay with this? I hope. Okay. Okay. So now you could ask the question. Suppose somebody hands you a field theory. How many theta parameters does it have? Right? And this is a question that people asked a long time ago. And a combination of physicists and mathematicians have answered this question. So, so physics and math people, okay, classified all possible thetas. So when I say physics and math people, who do I mean? I mean on the physics side, Nati, for example, Kazuya Yonekura. On the math side, there is Fried and Hopkins, and all sorts of very high-powered people. Okay, so I'm putting that up there the sort of argument by authority. Okay, so these are very serious people, and they proved very serious theorems to the point that mathematicians put their names on papers. Okay, and so the result was that the classification uses some really heavy-duty machinery. Okay, and it's called Borda's norms. And at this point, probably half of you are thinking, "Oh, God help us! He's going to tell us about Borda's norms." Don't worry, I won't. This is probably the last time I'll mention Borda's norms today. No, almost. You don't need to know anything about it. Okay. The point is, there's some machine from math, okay, whose inputs are, okay, you feed it the collection of fields in your back integral, and it spits out all the topological invariants you can build up. That's all. Okay. Now it's a very sophisticated machine. It can spit out things that you would have had like infinite amounts of trouble trying to come up with yourself, because some of them are very sophisticated. They're vastly more complicated than this. But nevertheless, okay, that's the machine. There are experts in the room who know more about this than I do. Like I'm looking at Uya, for example, and Daniel. But yeah, that's roughly, I think, as I understand it, how it goes. Okay, so the claim is that's it. Now, there are two questions now you can ask. The first question is kind of philosophical. Should we be happy? And the reason that you might not be happy, or at least you might not be as happy as you could wish to be, is it relies on, what Lagrangian you use. Namely, given some physical system, it can have many different Lagrangian descriptions because of dualities, for example. And depending on the Lagrangian description, there are different fields. And this Borda machinery, depends on which fields you use. So let me give you an example, okay, just in case you're feeling this is a bit too fuzzy. Okay, take QCD, right, with non-massless works. Okay, we know it has a theta term, that one, right, built out of its thing. And what does it count? It weighs instantons by some phase. That's what its goal in life is. Now, suppose the system you're trying to describe is a bunch of light pions. One way to describe it is the path integral based on quarks and gluons. Then it has a theta term in this sense. But another perfectly valid description is using chiral perturbation theory. I'm not writing anything because I think everybody here knows what chiral perturbation theory is. Chiral perturbation theory is just an SUN signal model in 4 dimensions. It does not have a theta term, not in this sense, right? Of course, I'm not saying theta disappears. It's in there, but in a completely different way, right? That has nothing to do with instantons. It's just some phase of some mass parameter, right? So how the definition of theta falling out of this technology very much depends on which path integral you use. And yet, sometimes theta terms have really universal consequences, like interesting anomalies that can appear and whatever. So you might wonder, is there a way to define theta terms in the first place that doesn't use Lagrangian? So I don't have an answer for that question. That's very hard, okay? In a limited number of cases, they have an answer, but in general, they don't. Okay? But that's still very philosophical, right? So anyway, I find this a little bit uncomfortable. Now, more practically, are there counterexamples? Okay. Now, I just said these are famous people. They prove the theorem. Some of them are mathematicians. So how can there be counterexamples? Come on. Exactly. Right. So they snuck in some assumptions, and you can sail right through them and write a counterexample. But that's interesting. Okay. So that's what we did. We didn't realize it at the time. Okay. So it's not in the paper. But that's what we did in this paper. We didn't emphasize that one. So let me tell you what it is. Okay. So I want to give you a counterexample, and having given you the counterexample, which I'll do over the next 5 minutes or so, that will motivate trying to define another class of theta angles beyond the conventional ones to fit in this new theta angle. Okay. So the thing that I want to define, we gave a funny name. We called it a Cheshire theta angle. If you know if you've heard of the Alice in Wonderland story, this is some reference to a spooky cat who is almost invisible, okay? But he likes to disappear, leaving only his grin, okay? So this term kind of is almost invisible in the physics, but leaves his grin, okay? So let me tell you what it is. It can be defined in a very wide range of systems. I'm just going to pick the simplest possible example.
Sorry, can I ask one?
Go ahead.
Right, so theta in higher probability theory will just appear as a U1 phase multiplying the mass number.
Exactly.
Right?
Exactly.
And, okay, it perfectly satisfying 2-pi periodicity.
Yeah, nothing wrong with it.
In
Yeah.
that picture, it appears to be nothing to do with the topological quantity of the theory.
Exactly.
Okay.
Exactly. That's the point.
Okay, so I guess there is no within the higher probability theory. There is no way of.
There's no topology that you could support an actual instant time, right? Yeah. Good. So that's sort of the message, okay, is that what the theta term is apparently changes radically depending on your description. So that kind of seems weird. No, it's not that weird. I'm just saying you might not be very satisfied with the definition based on this because of that. I don't have a better one in general. So, okay, so here, what example could I give you? Well, some of us are particle physicists, so let's do 4D. I mean 3 plus 1, okay? And okay, it's going to be an exercise for you to come up with an application, or if you want one, look at our paper. We actually have a Pheno application, but I won't mention it today. So I have 2 ingredients. I have a compact scalar. Okay, so that's one ingredient, one field, and then I also have a Dirac fermion psi. And I want to give you a free field theory kind of example. Okay, so what's the action at the free field theory level? Well, I don't know, it's something like v squared over 2. The kinetic term for the compact scalar. I'm using differential form notation. Is that okay? I can switch to normal notation if anybody wants. Okay. And then you know, the Dirac Lagrangian, basically, right? You could throw in a mass term. I don't really care. Guess I won't write it. And then the thing that's interesting for me, okay, like this, is to write the following funny term. Oh wait, let me do it. Okay, good. That makes more sense than differential form notation. Okay, so what am I doing here? I'm in Euclidean space. I forgot to say it. In this entire talk, I'm going to be in Euclidean space. I will never even come close to Newcastle. That's instantons, right? So let's just do that. And that's where the I comes from. And then there's a parameter that I have with malice aforethought called theta. Spoiler alert, it's 2-pi periodic, but maybe that's not so obvious yet. And then I have d phi over 2-pi wedge star j. Okay, j is a 3 form, so this is like a legitimate object. Okay, so at least it's meaningful to integrate this in a format. Now I have to explain to you like why this thing is interesting. So let's do that. So before I continue, one thing that I want to say is whatever this is. Okay, let me give this a name. S Cheshire. Okay. It's not one of these. Let me make that sharp. Okay. This thing is constructed such that it's an integer on any field configuration. Okay. This thing does not satisfy that property because, well, You see, the how do I put this? This thing by itself integrates to integer on shell, right? But off shell it doesn't have to. So on random field configurations, it can do whatever it wants. So from that perspective, you might say, like, why should theta be 2 periodic? I've said that it is going to be, like, why? In which instance of theta? So I have to explain that. So let's see that theta is 2 periodic. Yes.
It seems that as long as the term in your square is the top form, it's okay.
Say that one more time. It is a top form, yes.
Yes, so it doesn't matter if to be a fermion field or boson field.
Yes, absolutely. This I picked an example with a fermion. Okay. It could have been a boson. If it had been a boson, there would have been an extra subtlety. It would have been so. The same thing can be defined, but feel free to ask me later. Okay. Conceptually, everything is the same. At a technical level, there's a slight difference, and I can talk about it later. But it's fine. Okay. Basic. Okay. Let me know. Okay. So y is theta equivalent to theta plus 2. So the way to see this is the following. Let me define a quantity that I'm going to call A effective. There's no gauge field here ultimately, right? I mean, I don't have a gauge field as part of my fields. I'm going to define an effective gauge field, which is defined to be theta over 2 pi. So far, so good. Now, in terms of this auxiliary definition, my term over there is I theta, whoops, not yet. A effective wedge star J. Right? But this guy is a conserved current. This is the coupling of a gauge field to a conserved current. By the way, now it's very easy to see why the scalar is subtle, right? When you have scalars and you couple to gauge fields, there's an extra Seagull term you have to worry about. I don't want to worry about it, that's why I'm using a fermion. If you could worry about it, then you could fix it. Okay. Anyway, let's stick with this. So again, I want to emphasize there's no actual propagating gauge field here. This is just a trick, just a name for some term. Okay, but staring at this thing, remember J, the way that it comes out, it's just a conserved current. So let's ask, what happens to A effective if I shift theta to theta plus 2 pi? Well, A effective changes by that, right? Stare over here. Now that's interesting, because remember, pi started its life as a 2 pi periodic field. And this is a U1 conserved current. Therefore, this should be a U1 gauge field. And if there's no 't Hooft anomaly, with a U1 gauge field, if you do a gauge transformation by some 2 pi periodic parameter chi, that leaves the partition function invariant, assuming there's no 't Hooft anomaly. And here, there is not, right? Therefore, if you use phi as your gauge transformation parameter, the partition function and all correlation functions do not change when you do this shift. And therefore, theta is 2 pi periodic. So it's a completely different argument for periodicity than normal. Okay. So when the mathematicians were proving their theorems, this is not what they were thinking about. But it's a 2 pi periodic parameter. But the definition we heard this morning, right? It appears multiplying a term in the action. What more do you want? Okay. So it's some kind of theta term. Now you can ask, what does it do? Because I have to tell you, the reason nobody in their right mind wrote this until last year, as far as I know, is the rules of effective field theory say that you're not allowed to, you shouldn't write things in the action that can be eliminated by lower order physics of motion. And if you naively integrate display parts, you put the D on this, it's 0, so you might want to throw it out. But that's very hasty because phi is not globally well defined. So you gotta watch out. So that suggests that something interesting will happen with vortices, right? That's where the non-well-definedness of phi by itself is in vortices. And in fact, if you calculate e to the I integral A effective on some curve, in general, you will get e to the I theta if there is a vortex inside C. That makes sense? Now, what does that imply? It implies that theta gives an Aharonov-Bohm effect for psi particles. Right. So when these, if you turn on this funny term, then when the psi particles go around vortices, they pick up a phase from the Aharonov. This thing is visible. It does. It induces scattering. Whatever. It's nice. So the point of this is not to spend the entire time talking about this particular example, but just to say, people claim the theorem. I don't know, remember, did I erase it maybe? Yeah, I think I erased it. Okay, but there's like a counterexample. So now, the counterexample, of course, goes through relaxing some assumption. So the thing that we should now ask is, okay, can we define like some kind of generalized things? And then also if that include this counterexample, and if so, how are they related to the normal data? And let me tell you the punchline in a picture. So here are the standard theta terms. I'm going to call them Lagrangian thetas. Okay, so prime example, theta Yang-Mills. Okay, so those are the conventional ones. So what I'm going to try to define today, and is defined in this paper with Maria and Shi, is something else, which we're calling symmetry theta angles. So their definition is through symmetries, not through the Lagrangian. And we just saw the first example. Okay. But there are many, many, many more. Okay. And oh, I should tell you one other example that lives in this overlap, which I'll then tell you about in a second. Right here, there is the Maxwell. It's possible to think of it as a normal theta angle, of course. That's where we will learn about it. But it is also a symmetry theta angle.
But the symmetry theta angle can also be written to the Lagrangian.
Sometimes. That's what, see, there's an overlap region.
But Cheshire was also that you can.
Good, good. When I mean, oh, perfect. Thank you for highlighting this. When I say Lagrangian theta angle, I don't just mean that it can be written as a term in the Lagrangian. I mean that it is defined, as the integral of something manifestly topological, right? That conventional notion of theta angle, that's classified conventional of many words of the field space, of the homotopy target space, whatever. I know that's confusing. Okay, so there are definitely theta, Cheshire theta angles that can't even be written like this. They're just weird. Okay, in some cases they can be written like that. In some other cases, they can even take the same form as Lagrangian theta angles, the degeneracy of this picture.
And also for this Cheshire theta angle, if the U1 current that you're coupling to the axion in this case,
yeah,
a self anomaly or any other anomaly, then still this term is acceptable as a Lagrangian term. You just lose 2 pi periodicity of theta.
Hold on. If this thing has a self anomaly,
yeah,
then yeah, you lose the 2 pi periodicity of theta, and I don't have a nice interpretation of it. Right. If there's a mixed anomaly with something else, very interesting things happen, and basically that's where the Witten effect comes from. Okay. The one that you know a lot in the Maxwell. But yeah, bear with me. Okay. In fact, you might have heard about that from Maria. Maybe she didn't use those words.
No,
something else. Okay. Good. So yes, please go ahead.
said, J is not, or J is conserved, but clearly it's a metric that's R properly, so it's not conserved. And then you just over here.
So what do you mean it's not conserved?
I'm sorry, it's conserved, but it's not topological.
It's not topological, yeah. The conserved by the equations of motion.
Right, yeah, and you said, well, it looks like a gauge theory. We're fine with that. But is there sort of a more formal statement? Like,
Oh, absolutely.
like I'm missing something, and it'd be great.
Well, so while I am looking at the time and I'm not going to get there, in a different world, if I were to get to this point, okay, the statement would, I'll just make the statement and then, okay, the Cheshire theta is a U1 0 times U1 2 symmetry, yeah, symmetry theta angle. So this has a very general non-Lagrangian definition as a theta angle associated with this global symmetry. I haven't told you how exactly, but so who are the ingredients? Okay, this global symmetry is the one related to this current. This global symmetry is the one related to d phi.
So you were just trying to say that, like, since we know it's a current, it has special properties.
Yeah. But it's ultimately because it's all types of symmetries. And there's like a machine that you can hit this symmetry with and produce a thing that with a particular representation of the pattern of fields, maybe those fields, gives you this term.
Can I also ask another?
Please go ahead.
Maybe time to speak.
As many as you like.
Okay, great.
Yeah.
You took U1 times U1 gauge theory.
Yes.
And you wrote down a kinetic mixing term that's
Yes.
imaginary.
Yes.
Is that?
Yes. Yes. That one is also a kind of Cheshire theta term. Gongdun is working on those. They are interesting for dark photon models. There's some interesting things in that. They're interesting for many reasons. Yes, we should talk more. Okay. In principle, we're also talking to Gongdun about that. In principle involved, but Gongdun is very fast, so I'm not sure where he's with that project. Okay. But other questions before I try to define symmetry theta angle? No? Okay. Is the pace right, or am I going too slowly or too fast? All right. All right. Okay, so I'll keep this. Maybe this is motivational, so I'll keep it as well. All right. So I think to define these funny generalized theta angles, it would not be very illuminating if I just told you a definition. So I want to try to motivate it and then give the definition. So to motivate it, what I want to do is I want to spend a bit of time sort of reviewing what Maria talked about, but in faster and with highlighting different aspects, namely stuff to do with the Maxwell theory. So I apologize to those of you who were here last week and followed every single word of Maria's talk, which I'm sure all of you did. So what can I say about the Maxwell theory? So here's Maxwell theory. Okay. And well, the theta angle in Maxwell theory has a very famous consequence. It drives a Whitton effect. Right? Some people don't normally put this adjective in front because there's only one Whitton effect, right? The one that Mr. Whitton came up with. But we will see, right? So I want to call it the charge Whitton effect. Okay, just for short. So we all know what it is, but let me just write it down. So if you have like a Wilson line, whatever, line operator with labels E and M at theta equals to 0, and you think of this as the physical electric charge and the physical magnetic charge, the things that you would read off from freshman level electromagnetism, like first year electromagnetism using the Gaussian surfaces, Okay, that's what I mean by the E and M charges, the capital ones. When you turn on a theta angle, this electric charge gets fractionalized by the magnetic charge. I think everybody knows this from like the first class or the second class on field theory. Okay. Any questions about that? You want me to say it again in a different way? Okay, well, even if you don't want me to say it a different way, I will, because I need to for what I'm about to do. So here's a different way of seeing it, which is going to help me connect to what I want to do. Okay, so the different way of doing it is, so let's think about the correlation function that involves an 't-Hooft line operator. So this is an 't-Hooft line operator with magnetic charge M on a curve C. And the correlation function is calculated when the space-time manifold is like R4 or S4 or something like that, okay? If it's more complicated, then what I'm about to write won't be quite correct. With those manifolds, it won't be. And okay, so we start with a theory with theta equals to 0. Oh, sorry, theta not equals to 0. And now you can ask yourself, is there a way to relate this correlation function in the theory with theta equals to 0 to some correlation function involving an 't-Hooft line operator in the theory where theta is 0? The answer is this. Okay, so bear with me for a second. Okay, so there's a way to like do a computation to prove this. I'm not going to do that. Instead, I want to motivate. Suppose you believe this statement, because you've seen it an infinite number of times, including during this conference or workshop. So what is this? So let me suppose I'm an informal person, and I'm not very careful. And heuristically, I say to myself, look, what is this integral over? It's over some disk, where if this is C, the disk is the interior, right? And at the loosey-goosey level, technical term, this is basically use Stokes' theorem, right? And this is just like e to the I theta m over 2 pi integral A, right? A little naive. Loosey-goosey because there's like singularities and you can't really use this. But anyway, roughly speaking. And then you stare at this thing and ask, what is that? Well, it's an improperly quantized Wilson line, which is the thing that you would get if you had a fractional electric charge of that charge, right? And that's just this thing. So that's a way, if you know this result, to get to that. Is that okay so far? Now, where I want to go with this is different. Okay. So the thing is, there's another way of looking at this. So far, I've been highlighting things to do with the electric charges, both electric charges and magnetic charges, because I've been keeping track of both. But suppose I want to keep track of this, only ever talking about stuff to do with magnetic charge. Well, that's not very hard. In fact, the way this came out in the first place, only stuff to do, with M's was floating around. And what is this thing? Well, e to the I alpha integral dA over 2 pi on some surface, that's the generator of the magnetic that's the generator of the magnetic one-form symmetry, right? So here, what just happened, okay, is that by messing with theta, we're like dressing 't-Hooft line operators by surface operators made out of the magnetic symmetry operator. And if you hung around with string theorists long enough, you'll know that they call that twisted sector operators. Okay? So, relatively, if you stick the theory on some less trivial manifold, like your space-time is maybe S2 times S1 times S1 time, just for the sake of argument. Okay. You know, time evolution on this gives you Hamiltonian with this thing as space. And this is space. And this kind of statement is equivalent to a fairly clean statement about Hamiltonians, which is the following. If I have a Hamiltonian in the theory with theta turned on, where space is this, which Hamiltonian you use depends on which space you're using, in principle. Your Hamiltonian could be in some twisted sector. So it might be a Hamiltonian of things that are acting on things that are not genuine line operators. They're attached to surfaces, and they carry some charges. So this is what's called a twist. This is a charge. The charge is probably fairly easy to keep track of. It's basically how much flux is associated with your twist line. The twist is a little harder to visualize. It's related to what kind of twisted boundary condition you need to activate for some background field on the spatial cycles that don't touch the thermal cycle. Okay, but that's in general some 2 pi periodic parameter alpha.
That alpha, anything to do with that alpha appearing there?
No. So, right. Yeah. It's just like basically it's the holonomy of a gauge of a background gauge field that you stick on S2. And now you can try to ask, how is it related to a Hamiltonian with the same charge, 0 theta angle? Okay, so sorry that I'm writing it small, but this is theta over 2 pi times n. Okay, so this statement is related to that statement over here by setting alpha to 0 from the very beginning. Okay, so alpha is 0 from the very beginning. You start with somebody who's a genuine line operator, it becomes a non-genuine line operator with a particular twist. Okay, you may be wondering, where am I headed? Bear with me. But before I tell you that, questions? Yes, go ahead.
I have a question about your set angle. So in your case, for the set angle, so is CP important? So for example, so in the ordinary set angle with theta FHF, so FHF varies the
Yeah.
So but in your
I haven't said anything about CP yet, right?
CP,
Yeah. So if you impose CP, then it will pose some further restrictions on what the allowed values of some parameters I'll introduce are in some cases. But I'm not going to assume I have a CP symmetry. Yeah. So I will ignore space-time symmetry entirely. Yeah. These are just to take into account. We can talk more later. I'll only ever put my theories on orientable manifolds or spinable manifolds. I won't think about pin. And I won't even do what I just said, in case you're worried. It's in my head when I think about this. Pins never appear. Okay, so good. Other questions? All right. So let me try to summarize what just happened, though, because that's going to be the jumping off point for the generalization. And by now, I know for sure I'm not going to get the continuous ones. That's okay. There's enough interesting stuff to say for this week. So, so how can we summarize this? So, Maxwell theta, what it does for a living is it shuffles the twisted sectors of fixed charge with respect to U1 to the magnetic one from symmetry of Maxwell. Okay. So let me call that's what's happening over there, right? And that's what's happening over here. So in Maria's talk, this is what was called the topological width limit. And what I want to now emphasize is that the standard Witten effect due to Witten in 1979, to define it, requires two symmetries, the electric symmetry and the magnetic symmetry. But, you know, this one only requires the magnetic symmetry, and that's if it's more robust. This one makes complete sense if you obliterate the electric symmetry, destroy it. With the normal Witten effect, the charge Witten effect does not make sense if you destroy the electric symmetry. Okay, so anyway, this is like a consequence of the theta term, which I am certain is well known to the experts, but people don't really emphasize it. We couldn't find anybody who emphasizes it in this way. Maybe somebody does, but we haven't found it. Now, the idea is, well, if I had infinite amounts of time, which I don't quite, despite 2 hours that the organizers generously gave me, I would now go and I would show you that the Cheshire theta term does exactly the same thing. It also mixes up twisted and vacuum sectors with fixed charges, but you know, it's all more complicated because there's like two symmetries involved, and they have funny form degrees. It can be done, but you don't want to see it. Trust me. But it's the same basic result. So, inspired by this, having done that computation, we had the following idea. Could we try to define a generalized theta angle by this kind of statement? A generalized theta angle is a thing that shuffles twisted sectors of fixed charge with respect to some symmetry. So,
Aleksey?
Yes.
So great. So I understand that then you're taking the interpretation of theta parameter that shuffles twisted sector this way, precise manner.
Yeah.
Now, is theta parameter of the Maxwell theory a super selection parameter, like in the Young-Mills case? So let me just say where I'm coming from.
Okay.
That
Yeah.
theta parameter of the Young-Mills theory has many different faces, right?
Yeah, as many different ways to talk about
Right, and the one way of introducing it is this unitarity, locality. You have to some particular way with this parameter, and it serves as a special sector.
Yeah.
So now, I understand that you're taking this face of the data parameter.
Yes, this is the one I need to generalize. Yeah. I have to confess, I haven't really carefully thought about the super selection perspective on this. So if I tried to answer, I would be making it up. So I'm not sure. Okay. If I have to guess, I would say that it will go through, but I'm really not sure because I really haven't thought about it. Okay. Yeah, thank you for asking that. Yeah, so let me try to now be a little bit more. 1 second. Yeah, go ahead. Yes.
So related to the idea about theta terms, what if the magnetic symmetry is spontaneous?
Oh, good.
Sorry, opposite. Sorry.
Good. It's even better.
Okay.
Maria, did you talk about it?
Yeah.
Okay. That's okay. I'm not trying to put you on the spot. Okay. But now you could ask. Okay, I don't know exactly which question you have in the back of mind. Would you like me to comment on what happens in that situation?
Sure. Yeah.
Okay, let's do it. So consider the charge 1 Gillian-Higgs model. Okay, and now you could ask, in the charge 1 of Gillian-Higgs model in the Higgs phase, what does the theta term of Maxwell do? Now, naive statement first. Okay, if you had asked me this question a year ago, I would have told you, well, obviously. Okay, because the only thing the theta term does for a living is it messes with electric charge. And in the Higgs phase, you completely obliterate electric charge, and there's nothing to discuss. Right? However, you don't obliterate this symmetry, so it's meaningful to talk about it. So what it does is it gives a generalized Aharonov-Bohm effect. You might ask for who. So I'll be able to draw it. And let me say it in words, and then if you push me, I will draw pictures and maybe write a formula. So in words, okay, magnetic vortex springs, they have a world sheet sigma, okay, get an AB phase, which is e to the I theta, multiplied by their magnetic charge in principle, let's say it's 1. When they move in the background, I'm going to do a line operator insertion. Okay. Now, what does that do? Physically, like more physically. Okay, this is still very abstract. Physically, if you have two intersecting magnetic strings, at the intersection, there's a phase of e to the I theta. Why? Now, this may be obvious to you, but for everyone, I'm going to say, just look at this thing. If you have a magnetic string, what's the defining property of a magnetic string? It's that there's a flux in the magnetic string. So here's the flux in one magnetic string. Here's the flux in the other magnetic string. They got to be intersecting so that both can be activated at the same time without giving you 0. And when that happens, the theta term gets activated and it decorates every intersection of the theta. So it does something.
In Euclidean.
In Euclidean signature, I have no comment on Minkowski, but we should discuss. Okay. But
weird happened for Cardin.
Huh?
Does something weird happen for Cardin?
Yeah, there are generalizations of this that will charge on this. It's relatively straightforward, although I have to confess we didn't talk about that case. Yeah, but it's kind of fun that you can do something for charge 1. Normally, the charge 1 is just completely featureless. It's completely boring. We heard some advocates for that point earlier, but it's not entirely boring. Okay, other questions? Okay. So there's also a way of squeezing a non-invertible symmetry out of this construction, but let me know. Because I'm after something else. So good. So this is like a definition, but I'm going to put a prime on it because it's not going to be my final definition. It's like an initial attempt at a definition of something. Okay. Because once we try to make it precise, we'll see that the precise definition is a little different in ways that are interesting. But like a tentative definition of symmetry theta angle is a symmetry theta angle for a G symmetry. Well, it's defining it by its effects is a bit awkward. It's not quite a definition in and of itself. You have to like put something after this definition, okay? But the thing that a symmetry theta angle for a G symmetry does is it shuffles twisted sectors of G with fixed B charge. It's a very tentative definition. We'll have to refine it. Okay. So all I did is I just replaced U1 with G. Okay. So one thing that has to be said now is to even contemplate this, the symmetry G has to be non-anomalous, right? Because like, what is a twisted sector? How do you get there? Is you turn on a background field for the symmetry. But that's only sensible and meaningful. The symmetry is not anomalous. If it's anomalous, all bets are off. You have to rethink it. So this is only going to work for non-anomalous symmetries. And also, I should admit immediately, while we suspect this can be made sense of for quite generic symmetries, we've only actually carefully worked it out for 2 cases, where G is a finite abelian symmetry, albeit it could be pretty complicated, but could be mixing of different form degrees, whatever, but still finite abelian symmetry, nothing higher group. We haven't worked that case out, or continuous. U1 symmetry. Okay. We haven't gone beyond that. We have not built in space-time symmetries into the story, nothing like that. It's just the first pass for the simplest cases. Yes.
About
the anomaly. So
Yes.
since what you really want to do is just a projection to the given charge sector, so really generic gauge fields are not necessary, right? So,
Yeah, not necessarily completely generic. You're flat is really what you want.
yeah, flat is sufficient, and furthermore, so if anomaly cannot be detected on S1 times something.
Yeah. So this presentation of it would be blind to anomalies cannot be detected on toroidal manifolds.
So those anomalies are still fine.
So no. So this tentative definition term is not powerful enough. There's a more general one that I'll give you soon.
I see.
And that one will have you really need to make sure there's no anomaly for a gauge term. Okay. So this is just a very tentative first pass, kind of the first inspiration. Then when you actually go to define it, you discover you need something a little more precise. Good. It's 3:50. You've all been sitting here staring at me for 50 minutes. Why don't we take a short break, maybe 10 minutes? And then in the remaining time, after the break, okay, I'll actually define symmetry theta angles for this case. And then I'll give you some examples. So my examples will be SU2 Yang-Mills. There will be SU2 n equals 1 Yang-Mills. And they will include the standard model. Okay, and then we'll see how far else we get. Okay, let's pause.
Okay, let's resume. So whenever.
All right. I hope you're all reinvigorated. I know I am. So let's dive in. So I want to actually define symmetry theta angles, at least in some particular case, for real now. And please don't worry, examples are coming beyond the ones you've heard of. So let's define symmetry theta angles for symmetry G, which is a finite abelian group. So for example, it could be some zero form part times some one form part times some G d minus 2. I'm not going to include d minus 1 from symmetries. They're pretty weird. I like them. I've written papers about them, but they're pretty weird. I don't know about them. And also, I'm very sorry. I'm not including minus 1 from symmetries here. They're also very interesting, but they're also pretty weird. So I don't want to talk about it. So I have enough weird stuff to say. Okay. So good. And so I want to try to define things in this case. And well, this all already looks pretty complicated. So let's just imagine I have just one symmetry, not like this combination of many symmetries, and see like what can we visualize a target? Like what should this thing do? And then try to figure out a way to define something that does the thing that we want. So let's visualize our goal using a spectral table. I have a suspicion that this has a name that's not what I'm using. I don't know what name it has in the community, so we called it a spectral table. But I'm 99% sure we're not, well, I'm 100% sure we're not the only ones to use it. So if you know what it's called, please tell me. I'm going to define it. So what I want to do is I want to imagine that this is a Z3 symmetry. And I'm going to be agnostic as to whether it's a zero form or one form. I don't really care what I'm saying. I mean, it actually does matter eventually, but that's the details. So in this situation, there are three possible charges, 0, 1, and 2. Right? And, well, there are three possible twists, 0, 1, and 2. So, okay, so these are charges. And these are twists. So again, as a reminder, I hope you know what I mean by charges. That's pretty familiar. A twist is labeled by the holonomy of a Wilson line built using a gauge field for this symmetry. But if it's a Z3 gauge field, then there's like 3 different possible holonomies. That's what they are. Okay. And now, if there are many ways to like fill in the entries, but like one way to fill in the entries is to say, look, I'm going to work on some manifold which looks like this. Again, for the sake of argument, you don't have to do it this way, but it's just for convenience. And then on this manifold, there are Hamiltonians with charge, charge A and twist alpha, right? Does that make sense? For any given theory. So I can fill in this table with those Hamiltonians. But that would look very busy. So I'm going to fill it in like this. So this is for a theory Z. And I'm going to say that this entry is called A, B, C, D, E, F, G, H, I. Okay? So A is H00 on M. B is H01 on M, and so on. Okay?
Can I make
Yes.
sure the definition? So here, so M also assumed to have some non-trivial.
Oh yeah, so you can define yes, exactly. The M has to have the right topology for you to be able to have this. Yeah, this is just like a device for highlighting the thing that I want to highlight. Yeah.
So if there are several cycles, alpha.
Oh, then it's much more rich. There are many more labels. Yes, absolutely, absolutely. That's right. That's right.
Also, can I make sure?
Please.
So then A means that you inserted the operator with the charge M, charge A.
Yeah. So for example, A could be 1.
Yeah.
Then we're talking about operators with charge 1.
Inserted.
Yeah. Well, it's the Hamiltonian splits into super selection sectors.
Right.
Right. Labeled by charges.
Yes.
And so these are the Hamiltonians that act under charge 1.
Okay.
Things that are created by operators that are genuine somehow.
Okay.
Either local or line or surface, whatever. These are not quite genuine. But with the same.
Turn on the background gauge.
Yeah. And get the non-genuine ones. Yeah. So you build this little table. And then what do we want? So, well, the dream, okay, is as follows. It's to generate some kind of shuffle of this table, acting within each column. That is legal. That depends on some parameter, which is called theta. So our goal is to define that, okay? And what it's going to look like is something like this. Okay. I don't know. It's possible I just wrote on a legal table, but that's okay. Okay. So the main point is like you shuffle things within each column. Okay. Now the problem is, or a potential problem, is random shuffles are basically guaranteed to be illegal. What I mean by that is that if you randomly shuffle things, okay, you're shuffling operators, some of which are attached to like surfaces or lines or whatever, and you could very easily violate locality, right? Because you always have to satisfy some generalized Dirac quantization conditions for locality in field theory. And if you just randomly shuffle these tables, like you're guaranteed to screw this up. So the question is, can we come up with some algorithm or some general prescription, which is guaranteed to always produce a consistent shuffle. It doesn't break locality, and also the most general such shuffle. And if we can, that procedure is a candidate for a definition of a symmetry theta. Okay. So how to do it right? Okay. And so what we're going to do is use some standard topological manipulations from the literature. I could say they are quite standard in a discrete case, although some of our interpretations of them are less standard. They are not so standard in a continuous case, but I won't talk about it. Sorry. Yes?
Are you thinking about locality or something more like a generalized notion of like SL2Z invariance? Like,
Good. It's very important to think of it as locality. I will comment on why not SL2Z. That is a great question. Basically, the short answer is in general, SL2Z has nothing to do with it. So all that much. Okay. Good. So that's what we're going to do. Okay. And it turns out that these standard manipulations, which I'm going to introduce to you now, are guaranteed never to cause almost locality, and one can argue that they give everything one together. Yeah, we should put them together in the right way. Okay, so how's that going to work? So the operations that we're going to talk about are something called S, something else that we're going to call S dagger, something that we call T. There's like 3 different operations that to define each one of them for you. So S is gauging G. Okay. So good. So what does that actually look like? So you sum. Okay, so gauging G means that there's a gauge field associated with this thing. Okay, let's call it A, right? So let's imagine this is a P-form symmetry, right? Then A would be a P+1 form. That makes sense? Or P+1 cosine form, whatever. And then you sum over all A's. The experts in the audience know this is a way of not saying the word cohomology. And then take your partition function, which is a function of these A's, multiplied by a phase. So let me just tell you what happened, okay? So I basically, you just integrate over the gauge fields. That's what gauging means. And in the process, you put in choose a phase as a discrete Fourier transform, basically. And in the process, see, to make sense of this, this integrand needs to be a top form. So you pick up a new symmetry, G hat, which, if this was a P-form symmetry, would be a D minus P minus what, 2 or something?
Yeah. 2
form symmetry. And good. So in the example of interest, the representations of G, basically, and more precise versions of that statement. But for example, if G is Z3, then G hat will also be Z3. But like if this is a P-form symmetry, this thing in general is a D minus P minus 2 form symmetry. They're in general quite different symmetries. Okay. Now we'll come to it in a minute, but modular group structures will appear when these things are the same type of symmetry. But in general, they don't. Okay, so that's what the S transformation is. Now, the S dagger transformation it's just the inverse. Okay, so you take Z hat as a function of A hat. You stick a factor on it. I'm going to screw up my signs almost for sure. You sum over the A's, you normalize, and what you get back is to the thing that you started with. So applying S dagger after applying S just takes you back to where you started. So discrete gauging is reversible. Okay. I think most likely many of us have heard this before. Okay, so then what do we want to do? Well, we want to define so symmetry theta angles are created by transformations that look like this. I'll try to explain why. Okay.
You didn't tell us T.
I haven't yet. Hold on, I will. But this is where I'm headed. Okay, so the way it's going to work is we're going to take our theory, we're going to apply S, then apply T, then apply S dagger. And that will define a symmetry theta angle once I tell you what T is. And also I have to tell you why it defines a symmetry theta angle at a conceptual level, and then do example. Okay, so good. So then I need one more piece of lore that you're just going to have to trust me on because I don't have time to explain it. But the lore, which is really a theorem, is that a G charge is a G hat twist, they're isomorphic to each other, and a G hat charge is isomorphic to a G twist. Okay, so if you've seen this before, you're probably nodding wisely. If you haven't, this may be deep magic, but it's true. So why is this interesting? Well, let's think about what it means. So these statements mean that S transposes spectral tables. Right? If you stare at this for a while, you could like relabel this as twists and relabel this as charges for G hat, and then turn your head, and that's what it does. Okay? So S dagger does it again. Okay? Just retranspose it. And now T to define. So, well, the effect of T, I'll tell you what it is in a second. Its effect is to shuffle charges in fixed twist sectors. Okay, so what is this operation that does that? So T is stacking with a G hat invertible theory, which is a G hat SPT. Okay, so if you've heard about these types of things, so a few of you have in the audience, this is like standard, you do this for breakfast every morning. If you haven't, I'm very sorry. Yeah, so there's basically, this is actually not that hard to see. If you want to see it done slowly, mechanically, such that even a nuclear theorist can understand it. Okay, look at our paper. That was the result of Maria and I torturing Xi until he explained it to us in a way that even we could understand. So it's well known to everybody who knows it, but we didn't. Okay? But anyway, it can be shown. Okay, so these invertible theory things, okay, they generate the most general possible shuffle like this. That's consistent with locality. That's a theorem from the topological field theory literature. Yes. Go ahead.
Does this statement make sense without S? I mean, it seems.
Oh, no, you should sort of define T without S first.
Sorry, I mean the charge twist statement. Like, if I insert a twist by a G hat operator, that theory doesn't have the G symmetry. So I don't understand.
It's an isomorphism, so it's like they're not equals is being overloaded. They're isomorphic to each other.
Through S.
Through S, yeah.
Okay.
Yeah.
And I was gonna say, I mean, the T is basically Bayesian invariant operator made out of the G hat.
Exactly. So mechanically, if you ask like, what does this actually look like? So what does stacking mean? It means you start with your Z hat theory, and instead of working with Z hat, you multiply it by some weird thing, okay, which is built out of the A hat fields. And if you ask what it looks like E to the I, and then there's like A hat and some cups and God knows what else. Okay, but roughly speaking, something like that. Until you get to a top form. In the simple cases, you can write it that way. And for the non-simple ones, you should ask somebody like, well, maybe Yuya or Daniel or somebody else. This one. Okay, or Maria. Good. So why is this what we want? Well, let's think about it. So step one, transpose the table. Step two, shuffle within rows. That's what this is. Step three, transpose again. In doing that, you will have shuffled within the columns. Okay? So basically, we have avoided having to solve a problem from the start by mapping the thing that we want to some standard operations. Okay? Standard in the FTH community, some subsection of it. Okay? So, good. So a shift of a symmetry theta angle is generated by applying this operation to your theory. Yes, go ahead.
Do you have something like C there?
C, charge conjugation.
Yeah, like I'm.
No. No, you could throw it in there if you feel like it, but no, the definition. Yeah. Now, I should also say, I have been very cavalier with signs in this talk because from an audience, okay? You have to keep track of them carefully. We tried in the paper. And that may help address it, depending on what you're worried about. There are some funny signs that make this make sense without it.
So I also, it looks really similar
To what?
as the
Oh yeah, I'm about to mention that. Good. I'm about to mention that. It looks similar, but I'm going to emphasize the ways in which it is and the ways in which it isn't. Okay. Bear with me and let me collect my thoughts. I haven't looked at this thing in a while. Remind myself what I was planning to say. Oh yeah, okay. Good. So I should probably put this in a box. So this is what a symmetry theta angle is. Now I want to emphasize this operation is defined very generally. You don't have to define it on m times s1. Okay. Now, if you're working on m times s1, you get this interpretation in terms of spectral tables and whatever. But you don't have to work on such things. It's defined more generally. If you do work on m times s1, the effect of this is to shuffle things within columns. And therefore, its effect is to produce a topological Witten effect. And since it's the most general such shuffle, it produces the most general possible Witten effect, topological Witten effect, for discrete symmetry. Okay. And if you want to know how are these things classified, the classification Okay, so classification of G symmetry, symmetry theta angles is equivalent to classification of G symmetric invertible theories or G symmetric SPTs, because that's what you need in the T step. Okay. And unfortunately, that also involves vortices, but that's the last time I'll mention vortices. Because in simple cases, you don't need any of that heavy machinery. Okay.
But if the purpose is to shuffle the twist sector of given charge, does G symmetry invertible?
G-hat.
G-hat,
That's very important.
is that the part has to be relativistic invariant?
We only considered relativistic invariant.
Yeah. But, but for the purpose of your original statement, can't we make a special attention to time direction?
That's just to get a Hamiltonian interpretation, but I'm always assuming that underneath I have a relativistic film. Okay, I suspect that you can like generalize parts of this in a relativistic case where the underlying field theory is not relativistic, but we haven't thought about it. Yeah, that's a very interesting direction actually, and somebody else asked me this question during the intermission. Okay, good. So now several people have already asked me, what about SL2Z? Well, those of you who know about SL2Z, you know why you asked, and for the rest of you, let me try to say why this question came up. Sometimes S and T obey the following relations. S squared is 1, and oops, minus 1, and ST cubed is minus 1. Okay. Now, when this happens, if you've been around for a while, you might recognize these as the defining relations for a modular group, provided you also say something about what happens to T. So for example, T to the N might be 1. Now, when is sometimes? Okay. So the two conditions that you need for this to happen are that G is really the same as G hat. Okay, it is far from guaranteed. Like, I don't know if I still have it on the board, but like in general, they don't even have the same form degree. In general, they're completely different from each other. Okay, but you need this to be able to make the statement. And you need one more thing, which is technical but important. Your invertible theory needs to be something called a quadratic refinement. So basically, if you've heard of things like the Pendragon square or something, it needs to be of that form. And that's not guaranteed to exist. Your invertible theory is not guaranteed to be of this form, but in some cases it is. Okay. Now, good. Now, having said all of that, and emphasizing that sometimes one of the most interesting examples in physics where higher form symmetries appear is 4D gauge theories with one form symmetries on spin manifolds, because we want to put firmness, right? Standard model has firmness. And then these conditions are satisfied. Because the dual of a one-form symmetry, discrete one-form symmetry in 4D is, again, a one-form symmetry of the same rank. And the invertible theories for a one-form symmetry on a spin manifold are precisely of the quadratic triangle form, if you know what that is. So then you do have these relations. In general, you do not. Okay. Does that address the question? So sometimes it fits into an SL2 structure.
So, but you don't know if S here always have to minus 1 because I'm engaging the transfer to motion theory.
Yeah, good. So now there's some convention choices, exactly what you mean by S, that you can mess around with. Sometimes, depending on convention, they might give you something like charge conjugation or something like this. This depends on your convention choice. So there exists a convention choice. If you want to know the details, see Appendix B of our paper. We go through it in horrible detail, where it's -1. just in general. But that's not the same convention everybody else uses. For general discussions. Good, so you're an expert, so have a look at our comments, then you may. Okay, so what I want to do in the remaining time is to just focus on this some, okay? Because it includes some very interesting theories. And so what I want to do, sorry, before I continue, I want to give examples. Before that, any questions? No, I've killed you with too much detail.
So
much use of the word vertical.
Then just understand this thing from the perspective of more formula theory of Maxwell. So in the Maxwell theory, we sort of pick the Z and subgroupable magnetic open symmetry and try to do that, including D2 vector.
Yeah.
Then I get discrete theta angle term looking from top down, right?
Exactly.
And that is now this.
Precisely. So the Maxwell theta term turns out to be a U1M1 symmetry theta angle. So when you gauge this symmetry or the discrete subgroups. Okay, now I haven't talked about the continuous case, but it really gives you the Maxwell term. By the way, funny thing, of course, Maxwell theory is the second one from symmetry called the electric symmetry. You could turn on a theta term for that. Yeah. That's fine. So there are two theta turn on, but not at the same time. Anyway, that's an interesting story we can talk about later. But let's stick to this. So, sorry, I should say, in the examples I'll tell you in a second, you will see why I think it's very reasonable to call these things theta angles. I'm going to pick examples where they connect to known theta angles, as well as being a little bit some new things. But the most obvious example where it hits you in the face that these are really theta angles comes in the Maxwell case, but then I would have to tell you how to do it for the continuous symmetries. That's more something. Good. So here's what I want to do. I want to talk about SU2 Yang-Mills, of course, in 4D. For once in my life, it's a 4D talk. No circles. After this, okay? Not really. Anyway, no, the circles are big. Okay. And those of you who know me, when I work, sometimes my circles are small, but in this case, they're big. And if we get there, I'll say something about the standard model. Good. So this section of the talk, I'm going to troll a little bit. Let's reread between the lines. Okay, there's a famous paper by some people we all know called "Reading Between the Lines." So let's revisit that. Nothing they said is wrong, but more than they said. Okay, so what do I want to say about it? Okay, so well, let's consider SU2 gauge theories. And actually, instead of considering SU2 gauge theories, let me consider gauge theories based on the Lie algebra SU2. And there's several of them. And we asked, what kind of line operators could they have? So if I label my line operators by electric and magnetic charges within SU2, there are three options. There is 1, 0. This is the Wilson line. There is 0, 1. This is a 12th line. And then there's 1, 1, which is some kind of weird diamond. Yeah? These are my three lines that I could have and now need to discuss. So Aharoni, Seidler, and Tachikawa made the following very nice observations around 2013 in the paper called Reading Between the Lines. So they said, okay, if we think about global forms of the QFTs that could have these line operators, one of them we're going to call the SU2 Yang-Mills theory. Okay, and we're going to identify SU2 Yang-Mills theory as the theory that has the 1, 0 line in its vacuum set. Okay, and under the Z2 one-form symmetry. And because it's a Wilson line, and we want to think of Wilson lines as being electric, therefore, let's call this one-form symmetry the electric one-form symmetry. Okay, this is the idea. So far, okay? Okay, so it's a flashback to 2013. Continue with the flashback for just another minute. Then they said, okay, now the theory that has the 0, 1 line under all the same conditions, okay, in the vacuum sector and is acted on by the one-form symmetry of its one. Sorry, it has the 0, 1 line in its vacuum sector and it's acted on by some one-form symmetry. We call that one-form symmetry magnetic. Okay, and this is the charge operator. We call that theory SO3 plus. They called it SO3 plus. And then there's another theory, SO3 minus. It has the 1, 1 line, okay, in its vacuum sector, and it's charged under its one-form symmetry. And well, because that one-form symmetry in particular, so this thing carries magnetic charge, so they wanted to call that also a magnetic one. Right?
This is SO3 plus sitting at theta to pi.
Yeah. And the way, good. This is useful. So they said that these are related by a shift of theta to theta plus 2 pi. Okay? Yeah, that's now, what can I say about this that hasn't been said a billion times? Well, actually, I'm not sure. But let me try, okay? Good. So one thing that I wanted to say, time for it? Yeah, maybe I do. I want to engage in a tiny bit of trolling. See, I think, okay, anything I say that's wrong or offensive is my fault, not Maria's, and certainly not she's. So, look, I think calling one-form symmetries electric or magnetic is kind of ambiguous, precisely in cases where you have a self-position. Let me explain why. People do it anyway, and I'm going to do it too, but it's sort of worth highlighting this kind of weirdness. See, the normal statement is if you start with a Z2 sort of electric one-form symmetry, and you apply S, you get a magnetic one-form symmetry. Right? That's the view. If you apply T, you don't do anything. It's just stacking SPT. You're not changing the nature of the symmetry. Right? But in a theory where this is true, either 1 or -1, the -1 just means slope the sign of electron fields. It's kind of meaningless, but it doesn't do anything. If this is true, look, there are an odd number of S's. So what do you say about this? I mean, who you call electric, who you call magnetic is a little bit weird. Okay, but okay, maybe you don't worry about it too much. But this is a consequence of having a multiple structure. It immediately makes who you call magnetic, who you call electric kind of fuzzy. But still, let's just continue. Okay, that ends the first part of the trolling.
Basically, applying the T operation to G2 magnetic brings it to, yeah, you call it magnetic, but actually G2 diode, right?
Yeah, it's tricky. It's tricky. Yes. So there's dionic, but I will use this language too. I just think it's a bit.
And the reason why that is
I mean, with calling it dionic, I don't know, right? Because hold on, I will draw some pictures which actually clarify why I think it's still okay to call it magnetic, actually, but also it's confusing. Yes.
In the n equals 4 static, there's no sense one is electrolyte sort of a branch.
Yeah.
That you then decide.
So good. That's actually closely related to the thing I'm about to say. Although I have no supersymmetry yet, and given the time I won't. Sorry. But yeah, there's like just a big family of theories. Any one of them is on the same footing as any others. You have to decide what to call them. But it's kind of fun. There's some physics in what you call them a little bit. Okay. So but let me refresh my memory on some notation so that I don't confuse you much. Okay. Here comes the first punchline, I guess, that I'll have today. So let's bear with me. So I'm going to talk about SU2 theories from now on for a little bit. And I'm going to be drawing spectral tables. And I'm going to label this by charges, these by twists. And this is going to be A, B, C, D. Okay, that's it. So I'm going to pretend like I'm working on a manifold, if this makes sense. Okay, just to have something to hang on to. And well, actually, imagine that this is really the thing that we're comfortable calling SU2 Yang-Mills theory. Then who is who? Okay, it's kind of useful to like write that out once and for all, and then I'm going to start drawing a web of theories connected to S&T transformations and tell you some interpretations. So A, right? It doesn't carry any charge under the one from symmetry, right? So it's just particles, and it's also not in a twisted state. It's just particles. Glue balls, right? So B are the Wilson lines, right? And then C are atomic lines, and D are diamonds. Is that okay? Now, diamonds carry both electric and magnetic charge. So actually, it's very nice thinking about whatever symmetry acts here as an electric symmetry, because look, it acts on things that carry electric charge. It's these. Just one of them is kind of weird because it's in a twisted sector, but whatever. Any questions about that notation? So now I'm going to draw a little web of 6 theories that are, in my opinion, in our opinion, candidate global forms for SU2. Each on the same plane. But you'll see. So first, let's draw A, B, C, D. Okay. This guy is SU2. So now let's apply S. So what does S do? S transposes the table. So we get A, C, B, D. Okay. Then let me apply theta.
T.
No. By which I mean theta. So I mean, hold on. So this is going to sound psychotic, okay? I mean this complicated composite operation, but it's actually not complicated in this case, because what does it do for a living? It transposes within columns, and it only does anything in the charged sectors. Remember how it worked in Maxwell? Like in the sector which doesn't carry any charge, doesn't do anything at all. So all that this operation does is it does that. It transposes these two. And now let's try to identify like who are these two theories. To go from here to here, what did we do? We gauged the Z2 electric symmetry. This is the SO3 plus here. Let's make sure that I haven't lied to you. Who is supposed to be charged in SO3 plus? The 'Twift lines and the diamonds. But the 'Twift lines are supposed to be in the vacuum sector. This is SO3 minus. Okay. In SO3 minus, who is supposed to be charged? I claimed that the one from symmetry in that theory is magnetic. Okay. Why? Dions carry magnetic charge, so do 'Twift lines. But who is where has changed. Okay.
But if we really perform SPS operation, then SOC plus go back, once it go back to SU, and T doesn't do anything. And
What? Hold on. There's a lot of degeneracies here. So there's also,
You have to take SU2, and then if you perform theta,
so if you actually perform STS, you will reach here. I guarantee. Okay, so hold on, let me fill out the rest of the table, then we see, okay? Because I haven't filled out the whole table. Okay, but I'm just saying that this is what's going to be the consequence. And in fact, this is one of the reasons why I think it's reasonable to think of this as defining a theta. So let's fill out the rest of the table. There are 3 more entries. Okay. If I apply theta here, theta transposes the charged column. So what do you get? So you get A, C, D, B. Okay. Who the hell is that? I don't know. Leave it alone for a minute. Okay, so then there's going to be. God, I don't remember the name. Hold on. Oh yeah, the 2 weirdos. Bear with me for a second. So S is a transpose again. So this is D, C, A, B. And this guy is related to it by another theta transformation. And this one is A, D, B, C. And now that I have one, apologies, now I want to point out that there's some relations. And so these 2 are related by T. You see the difference between them is flipping C and D. Okay. These 2 are related by T. I hope. Yeah, they are. It's a miracle. And then these 2 are related by T. And if you carefully track through this, I hope you will get the same answer there.
Get one more S line.
Okay. Okay. So it's time to collect our rings. So these are the famous ones. The others are longer. So who is this? Okay, so let's look at it. We called this SU2, and we called it having an electric one-form symmetry because it acts on Wilson lines. It doesn't act on the Hooke lines. Well, that's true here too. So I think if you want to call these SO3 plus and minus, you should call these SU2 plus and minus. What's good for the goose is good for the gander. And here, you're doing an STS or theta transformation to the magnetic one-form symmetry. And here, you're applying it to the electric one-form symmetry. If you are happy with this labeling, you should not complain too much about that labeling. Direct all complaints to Afaroni Electrical. They introduced this language, not me. Well, they introduced this language, but I don't see why they didn't introduce this one. Well, they didn't think about it this way, but they could. And then, well, these 2 are weird. Okay, there's no standard name for the global form of those. They're kind of dionic intrinsically. So, for example, the hell was B and C again? Oh yeah. So look, so here B and C are both acted on. So there's some kind of dionic symmetry. So here, so for these 2, the one-form symmetry is kind of dionic in the sense that it acts on both of these, but not on D. Why is that dionic? It's because 1 plus 1 is 0, 1, 2. So if a symmetry is dionic, namely it acts on both electric and magnetic, it's not going to act on D. So I don't know what to call those. We have proposed a name for them in our paper. You don't care what the name is, doesn't matter. Okay. It's just a name.
Question.
Yes.
So you record SU2 plus and the minus. Are they related by a shift of theta by 2 pi or
No. Good. So,
differences?
yeah, the generalized theta. They're related by a generalized theta angle. Okay. See here. Okay. There is a symmetry theta angle that relates them. The same thing is true here. Here, there is also a Lagrangian theta angle that relates them, and that Lagrangian theta angle is in one-to-one correspondence with the symmetry theta angle. Why does this happen? It happens, and we discussed this and proved it, it's a long story, but it happens when the symmetry in question is solitonic. Julius knows all about such cases. It's when the symmetry only acts on defect operators. When that happens, symmetry theta angles can also be written as Lagrangian theta angles. This is true for Hooft lines. It's certainly false for Wilson lines in the electric duality frame, which is the only duality frame we know without massive amounts of symmetry in those. Okay. So this perspective with symmetry theta angles is somehow more general, I would say. Questions?
In this case, there's no even a Lagrangian translation right now.
Well, we know how to, we can write a formula that tells you what to do with a partition function or with correlation functions, but it's not a simple term in Lagrangian. By the way, if you ask, what's the physical difference between these? That would be a good question. Okay, so it's just, remember the Higgs theory? The example that Daniel asked about? Same thing. When confining strings intersect, there's a phase of -1 in this. So this generalized theta angle, this is a generalized, I don't know. Okay, good. So in the last 5 minutes or so, yes, go ahead.
So that paper says that some for larger group like S or N for larger group, some of the line structures cannot be obtained by shifting the second hand.
Good. They have in mind standard theta angles.
Can you do that for?
But I think if you use what we mean by theta angle, we should be able to reach out. That's what I think. But we haven't carefully checked the generic N. This is a guess. Okay. But that's my suspicion. So if you do the combination of Lagrangian theta angles and these theta angles, I think you should be able to cover everybody.
But another way of seeing this table, just actually if I understand this table.
Yeah.
So if I go to the S line, basically
Yeah.
I want magnetic, I get the Z2, and then if I do the topological Witten effect, which is represented by theta H, you basically stop in monopole with the ion.
Yeah. You could say it that way, yes.
Okay, but then here you could have done it just electric picture, just you could have done some version of topological
Yes,
Witten
yes.
effect. That's
Exactly. Exactly. That's what it is.
Yeah, okay.
That's what it is. Yes. Yes. Good. So the punchline from this part, okay, is that there are really 6 global forms of SU2 angles. Now, I don't want them to talk about it, but if you go to theories with, say, massless adjoint pronouns, things get more solid in very interesting ways. And the specification collapses to 3 theories. So some of them become equivalent to others. That's very interesting. And if you want to know more, please ask me. But the main punchline, if you don't have, like, basically, the hero is fermion zero modes. That's what it looks like, or in backgrounds. But if you don't have such things, you don't have to worry about it. And you just have 6 global forms. Where is the 6 coming from? It's coming from the fact that SL2 Z2 has cardinality 6. So there's a web of theories connected by these S&T transformations. I should emphasize, there is no guarantee in general that these S&T transformations are in one-to-one correspondence with the ones that you get by manipulating the normal angle state of the set. They don't have to be. They could be, but they don't have to.
But so I want to understand that. So when applying T to SU2 plus, basically what is happening is when computing the partition function with particular field, extra d cup beta is
Yes, that's right. That's right.
So from the operator level, so when we consider the boundary of one-form symmetry
Yeah.
generator, then we can have a freedom of attaching Wilson.
Yes, yes.
And in both theories, they just exist.
Yes, yes.
So from the operator level, what is really the difference? So both are.
Well, the difference is who is in which sector. You see, so they're not I mean, they're not.
Yeah.
They're not quite the same theory. They're related by T. Okay. But
Both are anyway not a genuine line operators, right?
well, yeah. So the distinctions lie in the twisted sectors. Let's say it that way. The distinction between them lies in the twisted sector. In the vacuum sector, they look the same, but the twisted sectors are different.
But the confusion is, yeah, both belong to twisted sector.
A and B don't belong to the twisted sector.
Yeah, but
C and D belong to the twisted sector, and who is. So, yeah, so the difference in the twisted sector in the sense that doing T manipulates who carries charge within the twisted sector. Right? So here C is neutral with respect to the one-form symmetry. Here C carries charge with respect to the one-form symmetry. Remember this table. So that's a difference. Do you care about this? This depends on your application of interest. But they're different things. I want to, if it's okay, you can beat me up as much as you want in a minute. I want to finish with a comment on the standard model. Just, I've trolled you enough, but this is the final troll. Okay. So, about the standard model. So if you take this perspective, the standard model, we've had beautiful lectures on it by several people in the audience. Well, make Daniel happy. Okay. Oh, and I forgot. Okay. That's the Lie algebra of the standard model, right? And if you like put this into a gauge theory in the most dumb possible way, like the one that is in Peskin and Schroeder, for example, I think, you would say, look, there is, among other symmetries, there's a Z6 one-form symmetry. In fact, it's electric. Of course, Peskin doesn't say this, but I'm sure he knows. Or not. I don't know. Okay. But anyway, everybody here now knows that we've had at least 2 lectures that talked about it just this week. Now, of course, you could gauge it, play games with it. We heard about that before. But we could also play all of these games. Now, I know there are other symmetries in the game, but let's just focus on this one. What do you get? Well, doing S and T and whatever, they don't meet with each other, right? With respect to this symmetry, you get a family of global forms of the SM. How big is this family? You have to do this kind of thing. Well, it is this big. So this is PSL2Z2, PSL2Z3. I take their cardinality, multiply them together, and the answer is 72. So you thought your assignment was to distinguish between 4 different forms in the standard model. And I think your assignment, and mine, and everybody else's, if you want to join us, is to figure out which of these 72 describe our universe. Now, before you freak out, as I have freaked out, it may not be as bad as that, but if not, it's very interesting because it could be that some of the theories here are equivalent to each other. That never happens for free. It always happens as a consequence of a symmetry. We know examples where it happens due to a chiral symmetry. We know examples where it happens due to a non-invertible symmetry. Sometimes the non-invertible symmetry is very non-obvious. Like, well, typically it is when I'm there will be something discrete. So it is entirely possible that many of these are equivalent to each other, but that has to be checked carefully, slowly, and then whoever is inequivalent are the different inequivalent global forms of the standard model. And for each such an equivalent one, we have to figure out what experimental consequences there may be, and then proceed with life. On that note, I think I'm I'm 1 minute over time. I'll pass. Thank you.